Howdy folks. So in my previous video you would have seen a teardown of the Anova precision cooker. And of course I went over the hardware, but I didn't really talk very much about the software. And this was kind of the next thing I wanted to do because of course this is an embedded system. It's an embedded Internet of Things type device, and that's kind of where I work. And that's, I follow the philosophy that if you can't do what you want with the thing that you bought, then you don't really own it. And some people go as far as saying, if I can't run my own code on the device, then I don't own it. But I don't usually go that far because I generally just, I can't be bothered to hack things to that extent. But I wanted to, at a minimum, understand how the system worked. And so I started a little bit of an investigation, which was supposed to just be a couple hours, but it turned into basically a whole day. And to whet your appetite for what's in this video, it's going to be long. I just know that because there was a lot of stuff that I did in a short period of time. And I kind of want to go through what I did in what order, regardless of whether it worked or not, because I know a lot of people, when they show reverse engineering and stuff, they just kind of skip to the end. This is what I did and this is how it worked. But they don't really show you the steps that they took to get there. And I kind of want to go through that. A little bit expedited, but I do want to go through what I tried and what didn't work, so that you can see my thought process, at least, going through this. And so I want to go through that. And just to whet your appetite, like I said, I was able to break their sort of pseudo encryption on their API. And I've been able to intercept traffic to the device. And I have a full breakdown of their API, their protocol, that talks to the actual cooker itself over Wi-Fi. And I've written a little bit of Python code, and I'm basically working on writing a little Python server which will basically stand in place of the basically of their sort of cloud system, and I can therefore have my own API, and I can talk to the device, and I can write web apps or Chrome extensions or whatever to control the device rather than having to use their app, which is really ultimately what I wanted to be able to do with it. I don't like to get my phone out to figure out how much time's left on my food. I just, I'm on my computer. I want it to be right there on my desktop. So that's the reason why I sort of was driven to do this. And so I do have, everything did work out in the end. And if I haven't finished the server by the time this video goes up, I will put a link in the description after I finish it to probably my GitHub, where the code will be located if you'd like to take a look. So the first thing that I did was the easiest thing to do, and that was to decompile the Android app. And I know that doesn't sound like it's an easy thing to do, but due to the nature of Java bytecode, you can basically fully reverse the compilation process on Java applications. It's really useful for anyone who wants to reverse engineer stuff. So, and the thing is, you don't even have to install anything. There's websites that'll do it for you. So you just throw the APK at it, and it, chooches for a few seconds. You get a zip file, and there's all your source code. And of course, there's a whole bunch of libraries and stuff in there that doesn't really matter. Graphics stuff that they've used. But there's also the com.anova namespace, and of course, that's where all the interesting custom stuff's going to be. And I didn't really care how the app worked. The app was too high level for me. I mean, the last time I wrote Android apps was like Android 3, so I'm a firmware guy. I work low level. That stuff's not so interesting to me. So what I was really looking for was the API. How does the phone talk to the device? And I was pretty quick to discover that it's a JSON API and it's a RESTful API. And the other thing that I noticed very quickly was that the phone does not actually talk to the device at all. The phone talks to it resolves a DNS query for an API at anovaculinary.com, and it connects to that over HTTPS, and that's where the JSON API goes. So right away, I know that the phone and the device never talk to one another. So that was a little interesting. And I mean, it makes sense though, because they claim that you can use the device, you can check the status of your cooking when you're out and about or whatever. So of course, if they need direct connection, that's not going to work. So I immediately thought, okay, they're using their servers as a relay. And so I resolved it. I looked it up. It's in Amazon Cloud, so it's an AWS instance that all this stuff is going to. And the API is pretty basic, at least as far as REST is concerned. It's just you give it sort of a device ID, which is probably like the serial number or something, and then you give it a secret key, which is probably some sort of authentication token, and then you can query the device's status, and you can initiate what are called jobs. So basically, when you pick a recipe and tell it to cook it, which is a certain temperature and time, that constitutes a job. So that's you can sort of query job status and do that kind of stuff through their API. So the at least the high level is pretty straightforward. Going into what commands are supported, there were some interesting ones. You could query the speaker status, like the beeper status. You could query the time remaining, the temperature, the set temperature. You could get the calibration data. So I could see a few messages in there. But realistically speaking, I didn't really go into the Android app. I didn't look at how the secret keys were being done. I didn't really care about that because all I wanted to know was how it's talking to their services, and so therefore how the other device must be talking to their services. So with this in mind, knowing that there's an HTTP API from the phone to their Amazon Web Services, I thought, okay, well, are they using, basically, is it just a relay? Are they just relaying the JSON through their servers back to the device, and the device is parsing them? And so the first thing I did was I ran Nmap to do a port scan on the device. And all of the ports are closed except for one, and that is port 80, which is HTTP. And so I thought this was interesting. And so I sent it a request, and it immediately responded with a 401 basic authentication requested. And it took me all of about 10 seconds to guess that the username and password was admin and admin. And it logs you in successfully, and it gives you a 404. So obviously there's a little embedded web server. It's the way these little wireless modules work. The wireless module does the actual HTTP sort of handshake, and the device is just passed raw HTTP commands. So their 404 was actually incorrectly implemented as a 200. So you got a 200 status code, but the text says 404. It's kind of, it's sort of a necessary thing with those little IP stacks that you don't really have control over. But nonetheless, it responded. So I thought, okay, there's probably some sort of, this is clearly you're not supposed to be here. This is clearly some sort of development or, production test or something kind of interface to the system. So I thought, okay, there's a URL that you can get stuff at. And so I tried a bunch of them that I thought would work, and none of them worked. And I ended up actually writing a little Python script that tried 45,000 different common URLs for kind of administration and test and stuff. And none of them returned anything other than the 404 page, with the exception of requesting favicon.ico. If you request the favicon, you get a zero-sized reply. So that proves that they have at least some logic that's scanning for the URL and returning different content in at least one other case. So I'm sure that there is a page that you can access somewhere. I don't feel like they would take it out, but the search space of all possible URLs is just far too large to brute force at 4 pages per second, which is the speed I was getting. So realistically speaking, it's just not possible for us to figure out what it is, because it's probably something custom. And it's not a real web server. It's just basically doing a direct string match between the URL and some internal value in the flash ROM. And so if they don't match exactly, it doesn't return anything. So unless I could dump the flash, there's no way we're going to find what that page is. And so that was kind of a dead end, and I didn't really care. But it kind of showed me that they weren't using HTTP, at least. It wasn't a server. There was nothing that was connecting to it. So it obviously must be connecting to something else. And of course, to figure out what's going on, we really need a packet capture. And what better way to do a packet capture than with pfSense? So because, of course, it's got to talk to the internet, so it's got to go through my pfSense router. And there is a packet capture feature in pfSense. Basically, you can just provide the IP address of a device, either the server it's connecting to or the local device on your LAN, the IP on your LAN, which in my case I knew because, of course, it has a DHCP request to get an IP address. So I just said, give me all packets that originate or are destined for that IP. And I started a capture, and then I plugged in the device. And I started the capture first because I wanted to make sure that I captured its initial sort of handshake with whatever service it talks to, because I wanted to see the full conversation basically. And so I let it run for a couple minutes, unplugged it, stopped it, and stopped the capture, and then downloaded it as a cap file, and then you can pop it open in Wireshark. And for anything network related, Wireshark is your best friend. So once it's in Wireshark, we can see a few things right off the bat. First of all, of course, the first thing it's going to do is a DHCP request. That makes sense. It's got to get an IP address. And then the next thing you see is it creates a TCP socket with this IP address on port 8080. And so the first thing that's interesting is there's no DNS request. It doesn't do any DNS. It just directly talks to this IP. So the IP address this thing eventually talks to is hard coded into the device. So they can't change that in the future. So if that IP ever moves, the devices basically stop working. So that's nice to see. I mean, it makes sense because the wireless device that they have doesn't have DNS support. So they would have had to implement that themselves, which of course is far too much work for something like this. So they just decided to hard code it. It's not great design, but I understand. And the other thing that I noticed was, of course, the IP address that it's going to. Look that up. It's also in Amazon Web Services. It's another AWS IP, but it's not the same IP as the API that the phone talks to. So they have multiple instances in AWS. So one to deal with the phone, one to deal with the actual device, and they must be sharing data somehow in their internal infrastructure. So I started looking at the data, and I immediately noticed two things. The first thing is the packets are very small. We're talking like 40 byte packets or smaller. So there's not a large amount of data in each of these packets. And the other thing is that there are no strings. It is purely binary communication. So this isn't JSON, this isn't some sort of textual protocol. This is all binary. So because this is a purely binary protocol, we have to figure out how they're framing the data and figure out what the binary representation of those APIs are. And that, of course, is basically that became the focus of what I was doing. I wanted to reverse engineer that protocol. What I wanted to know was how repeatable are these packets? Basically, is there a timestamp in these packets? Is there some sort of random number in these packets? Are they encrypted? Is there a key that they're using? Does the key change? Is it symmetric? All those kinds of things. So what I wanted to do was just have multiple runs. So I had my initial run, then I basically did the exact same thing again, started up a packet capture, plugged the device in, captured it for a bit. And then what I decided to do was go into Wireshark for both of the captures. And you can find any packet that's part of the TCP stream, and you can actually do a follow TCP stream. And this allows you to basically see the conversation in whatever format you want. And so I output it as a hex dump. And then you can actually save that hex dump to a text file so you can sort of see it in a better context. And I did this for both of them. And then I popped open Meld, which is my favorite diff viewer, and I basically diffed the two conversations. And what I was really surprised by is the fact that there was so little that actually changed between the two conversations. And this is a major win right here, because the only thing that really changed between the two runs were a couple of bytes in this sort of repeating packet over and over again. And so my immediate thought was, these must be the current temperature of the device, because everything else was the same, and the only thing that was different was the temperature that it was currently reading. So, just from that, I've identified which packet contains the current temperature, and which bytes in those packets correspond to the actual temperature value. And so now I had sort of an in to figure out how their packeting and how their protocol works, because I have the temperature in degrees Celsius, right? I know what that is because that's what it says on the device. And if I can time correlate that with the packets I'm seeing, I can figure out how they're encoding the temperature data into these packets. And that was crucial in determining how they're doing their stream. Now, the other thing that I also noticed just by looking at these packets is there are a few things that we can sort of get out of the way right away. There's a few assumptions that we can make, and they seem to be pretty solid assumptions. The first thing is every single packet, both from the client and the server, begins with hex 68 and ends with hex 16. And every single one follows the same pattern, which means that it's very likely that 68 is a header and 16 is a footer, and that frames each packet. So that made sense. The next thing that I noticed was the next byte, the second byte in, it looks very uniform. It looks a lot like a command. I mean, if I was to write a packet, it would probably contain a command and then some data and then a checksum, right? That sort of is just sort of standard, right? So seeing how uniform they are and how repeatable they are and how close together they are, it makes sense that that would be a command. And so that was my first assumption. And I went through the debugging went through the breakdown basically assuming that that was a command, although it wasn't really relevant for the first part because I was only focused on what I thought was basically the readback of the current temperature. So given what I thought were the temperature packets, I have 6 bytes that I can't necessarily account for. So I'm just ignoring those 3 bytes because that's what I think they are. The 6 bytes, don't really know. Now, if I was doing this, there'd be a checksum at the end. So what I did was I got out some checksum algorithms, some common CRCs and checksums, and I tried to see if I could match the packet up to the checksum. So I took it from the beginning of the packet, including the header, the beginning not including the header, the beginning not including the instruction or the type of the packet, and none of them matched with any standard checksum or CRC protocol. Whether they were 8 bits, 16 bits, 32 bits, I couldn't match any of them. So either this told me that either there is no checksum at the end of the packet, which I mean, it's a little strange, but yeah, I mean, you could assume that they're being protected by TCP and all that stuff. So it's possible that there's no checksum. They could be using a CRC and they're using some strange seed value that's not sort of normal. That's also possible. And so therefore, until you determine the seed, nothing's gonna match, even if the algorithm is right. So I sort of ignored that for a bit. So now I turned to trying to figure out how they're encoding the temperature data. And for this, I actually need to know known temperatures and packets that definitely contain that temperature. So what I did was I would heat up the sensor on the device, I'd do a packet capture, and then I would unplug the device when it was at a certain temperature. And then I'd know that the last temperature packet in that packet capture had to be that temperature. And I did this a bunch of times, so I came up with a bunch of different temperatures. I would have liked to have perfectly sequential temperatures, but I had a bunch of different ones, so it was good enough for me to determine how they were doing the encoding. So basically, I just put them next to each other in ascending order in a little text file, and I tried to figure out if there was any patterns. And I would expect that first of all, this is a floating point number, so it's got 1 decimal place, which means that they could be doing this a bunch of different ways. They could be storing it as a fixed point number, meaning that it's actually, instead of, let's say 25.8, they're storing it as 258, and then the device is doing a divide. Or they could be storing it like an actual floating point number. They could be where they have, you have the mantissa and you have the exponent and the significand and all those kinds of things. You could be storing it like that. But that seems a bit weird, but it's possible. Or they could be storing it by byte position. So 258, they could be storing it like that. And I wasn't quite sure, but it didn't appear to be any of those. It appeared to be something completely different. There was no correlation that I could see. And so this pretty much solidified to me that this packet is either encrypted or it's run through some form of obfuscation algorithm to try and deter tampering with the data, which makes sense. So I first of all thought, okay, is it encrypted? And then I immediately said, no, it doesn't look to be encrypted, because when you look at the packets, there's a very clear pattern, right? There's this 71 byte that appears in all the packets. There's this A1 byte that appears in all the packets. When you look at the numbers, there's far too much order in these packets for it to be encrypted with any like proper encryption algorithm, which makes me believe that this is simply obfuscated with someone probably thought they were clever and they decided to do something to manipulate the bytes, and the data is just there. We just have to figure out how to rearrange it. And so that was the assumption I went into as I had to figure out what this obfuscation scheme is. So of course I have the hex here, but the thing is, whenever you're working with an obfuscation scheme, don't word of advice, don't use hex, because it's going to obscure a lot of stuff. Because the thing is, operations aren't done in base 16, they're going to be binary operations. So the next thing I did was I made a table which contains all of the same data, but in binary, as separated by bytes. And I put the decimal representation next to it. And so now I was trying to find patterns in these bytes, in the binary. And one thing that sort of popped out to me, which I didn't even notice in the hex at first, was that if you actually look at the upper nibble of this byte here, this upper nibble corresponds with the digit in the decimal place position, and it works for every single value, right? See, 289078898. It works in every single one. It's the upper nibble of this byte. That seems very strange, but it's there. And so that tells me right away, it's definitely not encrypted. It has to be obfuscated somehow. And, obfuscation normally takes place by doing some sort of like nibble swapping, byte swapping, reversal. That's another one. XOR was another thing that you see a lot, where you XOR the whole thing with some value. That works well because it's really easy. You think about this. This is being done by an embedded processor, which means they're going to be using very, very computationally cheap operations to get the maximum obscurity out of the data, right? So there isn't going to be any crazy math here. It's going to be binary things, bit shifts, XORs. Those kinds of things. That's kind of what I expect to see here. Swapping, I've seen instances where they take nibbles and they have some sort of translation table that maps them to different places, but usually just moving data around. There's no big crazy math involved. So I could, just by seeing this, I could sort of say, yeah, there's no encryption, there's no crazy math. And the other thing that I kind of ruled out just by seeing that was XOR, because if there was an XOR, we probably wouldn't be seeing this, because the XOR would remove that kind of order. So I didn't think that they were XORing the values. And so I was looking, and I really didn't see much. So I decided, I was trying to move nibbles around, trying to use other columns, other values, and trying to assemble the digits with the data that was there, and I wasn't seeing anything by nibble. So I decided to reduce the clutter, basically. So the 68, the 05, those are the same. The 16 is the same. The 71 and the A1, those are all the same. So there's only 4 bytes, that actually matter, right? They're the only ones that have changed as a result of changing the digits. So the digits must be encoded in those four bytes. So I stripped everything down to those, and I wanted to look. Basically, whenever you want to look for bit patterns, you want to look for counting. Counting is the easiest thing. Binary counting is the easiest thing to identify in a bit sequence. So I had a couple sequential values, right? I had 19.8, 19.9, 20.0, and then I had 20.7, 8, and 9. So I had some sequential values, and I had a sequential value in every single position in the decimal number. And that is super helpful. So like I said, I noticed the counting for the decimal place digit, and I knew where that was, and so I marked that. The next thing that I noticed was going from 19.9 to 20.0. there was this shift over here, which could be a count. I mean, you're moving from one position over to the other, so that could be a count. So I marked those 2 bits as being part of that digit. And similarly, I wanted to find where this other digit was, the ones column. And so I looked at the 25.8, and the 5, there's only one 5 here, and 5 is 101 in binary. So I looked for 101, and you'll notice that 101 only appears down here. So which means these 3 bits must be part of this 5. It's the only way, unless they've done anything weird. And so I noticed, okay, there were these 2 here, these 3 here, and these 4 here. And I immediately thought, okay, well, if we want to get these back to their original values, we have to align the least significant bit with the end of the byte, which means we need to shift the byte over by a certain number of places. In this case, we have to shift it by 1. And in this case, we have to shift it by 2. And in this case, we have to shift it by 4. But wait a second. I deleted that column in the middle when I was trying to, make things simpler. So wait, this actually makes sense now. If we start from the beginning of the data and we shift by 1 bit, and then the next data byte we shift by 2 bits, the next one we shift by 3, the next one we shift by 4, the next one we shift by 5, etc., etc. If we do that, then they all align. All of the things that all of the bits that correspond with the values in their places correspond with, they all line up with the least significant bit. And so if you look at this now, and you take the lower nibble of each of those bytes, and you turn it into hex, you look at the lower nibble, it corresponds. And I did it in this file here. I did it for the number 20.0, and you can see here 2, 0, and there's an E, 0. And so that's 200. That's the 20.0. That's clearly the number. It's in order and everything. That's clearly it. But of course, there's all this data in the upper nibble. What's going on with the upper nibble? And of course, whenever you see values in the lower nibble, you immediately think ASCII, right? Because ASCII, they purposefully lined ASCII up so that the lower nibble was the value and the upper nibble basically just put it in the ASCII sort of namespace, the sort of the bit positions in the table. So if you actually decode these bytes, these 5 bytes, as ASCII, you get 20.0 carriage return. And as soon as I saw the carriage return, I immediately knew this was their obfuscation scheme. Because that's too perfect. It's ASCII. It's just plain text. It is actually a plain text protocol. They're just obfuscating it by bit shifting. And in fact, they're not actually bit shifting at all, because I had some, I should have mentioned that. I actually assumed it wasn't just a bit shift. I assumed it was actually a bit roll, because you have to move the bit on the least significant end. You have to move them to the other side. So they're actually rolling the bits around by n rather than just shifting them and shifting in zeros on the left. They're actually rolling it around. But nonetheless, it's basically the same thing. So now that I knew this, and they're doing this different bit roll for each position, I decided, okay, well, the first thing that I noticed, I guess I'll mention it. The first thing I'll notice is the sort of packet identifier, that ID, that command byte, the second byte that I thought originally. If you sort of follow this scheme, right, you follow the one, this side would be 0. So that makes sense. If it's shifted by 0, then it's not obfuscated. Or if they've just decided not to roll that, then that also makes sense. So it sort of made me pretty sure at that point that this was sort of some sort of like ID or something. However, at this point, there was one thing that I still didn't understand, and that was what this last byte here was before the 16, which was the footer. Because this, when you decode it as ASCII, doesn't make sense. It's just random characters. And so this made me think again, okay, well, wait a second. This looks like a checksum, right? It doesn't fit with the data, so it must be a checksum, but it didn't fit any of my checksum algorithms. So I decided to basically rerun the checksum algorithms on the non-bit shifted values, and they all still failed. None of them worked out. And so I actually determined their checksum algorithm just by basically by accident. Basically, if you add all of the values in the packet, including the header, all the way up to the position of where the checksum would be inserted, if you add all of those numbers up, and then you AND them with 255, you get the value in this second last position. So basically, they are just adding all of the bits together, and then they're just basically chopping off everything above the 8th bit, and that's how they're doing the checksum. So they're not doing proper modulus; they're just ignoring anything that overflows, which is fine. I mean, that makes sense for an embedded system. So that's how they're doing the checksum. So now at this point I was golden. I had ASCII coming out of it. I had the checksum calculated. I've got what looks like the header and footer and command all done. So of course, as you would do, you write a Python script that does this for you, and you feed it the entire stream of data. So basically, I went back to Wireshark, and I followed the TCP stream as I did before, and I exported it this time as raw. And one thing that you should note is you can't use the Save As button when you use the raw, because it doesn't actually save it in the same manner. It actually saves the bytes to disk. And if you want to interpret them as hex values, which is what I wanted to do, I just copy pasted the output into a text file, and that was my raw data. And we lose the ability to see which came from the client, which came from the server, but as you'll see in a moment, that's not really relevant. So I've got one thing per line. I wrote a little Python script. It parses out the lines, and then it even calculates the checksum, and it prints the ASCII values of what it's decoded after the bit shifting using this line here. This is the magic line right here. This does the bit shift. Because in Python, there's no way to really roll bytes as far as I know. So I just do a bit shift, and then I OR it with an ANDing of the lower bytes, bit shifted up by basically the byte minus the number of bits we're shifting. So that's basically how I'm doing the roll in Python. I'm sure there's probably a better implementation, but whatever, it works. And so once you do it, you run it, and you get this wonderful dump. So you can see clearly everything is plain text. And I mean, just look at how beautiful this protocol is. I mean, it's all text. Read unit, it returns C for Celsius. Read timer, it returns 0 minutes stopped. Speaker status, speaker is on. Then it's got this get number, and I've redacted the response to that because that's some sort of unique identifier for my device. And so I don't want people to know that. But it asks for the status. It says it's stopped. And then there we go, read set temp. And then it gives the set temp. In my case, it was 71.1 at the time. And then there you go, read temp. And it returns the value 20.0. So clearly we can see, and it just repeats. It just repeats this over and over again. So clearly the server is sending these commands, and the device is just responding with some plain text to this command. And so this is great. I mean, this is really great. But I noticed that there was a mistake here. I noticed that something didn't make sense because I was looking at the command value, and the command value of 10, it didn't match up with the data, because read temp and read unit both have a command of 10. And of course, if they're different, then why would they have a command of 10? That doesn't make sense. And so I just by looking at it, they both have the same number of characters. Right? They're 9 ASCII characters plus the carriage return. They're 10 characters each. Oh shit, it's a length value. So the second byte is not a command, it's the length of the packet. So I just modified my script, and at this point, I have everything working, and I can validate everything. In fact, one of the dumps I actually had a checksum failure, and it's not my script that's wrong. There actually was corruption in the data, obviously on the device itself, and it happened right when I started the unit up. So I wonder if the surge or some EMI when the pump started or the heater started up caused some sort of interference that corrupted the data. between the wireless module and the processor. So seeing that and seeing the checksum fail was a really reassuring sign that this was fully reverse engineered. So of course, once I know this, and I mean it's such a simple protocol, of course, now I want to write up a Python script that can speak to this device, and then I can basically get the script to tell it to do whatever I want. I can build my own API, build all my own stuff. But of course, we have that one problem of the fact that the device contacts this fixed IP address, which corresponds with the Amazon AWS instance. And of course, we want it instead to connect to my own machine, but we don't have the ability to change that IP address. So of course, what are we going to do? We're going to use pfSense to solve this problem. And you can rewrite the IP address in a packet in pfSense using the load balancer service. And the load balancer service, the point of this, what it does is you can basically create a pool of devices, and they can all have different, of course, they'll all have different IP addresses. And you can then create what's called a virtual server with a certain IP address. And then any request to go to that IP address, pfSense will balance it round robin or whatever across the IP addresses you put in its corresponding pool. And that way, if you have a bunch of web servers that are all serving the same content, it will sort of randomly or round robin distribute the load across those multiple physical servers. And it's a very convenient way to do load balancing. You can also do failover with it. So if one of the machines goes down, you can, it'll just redirect the traffic to another machine. But what we can do is we can create a pool which contains just my workstation or just my server, which is just the IP address I want things to go to. And I set it up on port 8080. And then I create a virtual server which has the IP address of the thing on the internet that they're talking to, the Amazon instance, on the same port. And so that way, whenever it tries to connect to that IP address, pfSense sees it as, oh, I should load balance this, and it then redirects it round robin to the only IP in the pool, which is my workstation. And as a result, all the traffic that goes that this thing has goes through my workstation instead of going to their AWS instance. So now I proved that this worked, first of all, just by powering the device up and turning the app on, and it couldn't see the device wasn't on, the wireless light wasn't blinking, it clearly couldn't get a connection. And then so I wrote up a little quick Python script that created, just opens up a TCP socket, and it starts by, it just spews out the ask what the device ID is, and it got a response, and it was able to decode it. So at that point, pretty much it's just a programming exercise to write the server. So that's what I'm currently doing, and I will put that out, like I said, on my GitHub whenever I get a chance to finish it. I'm supposed to be doing work, so I should probably stop with the reverse engineering and get to my real work, but I will get it out probably within the next couple weeks or so. So check back for that if it's not out when I publish the video. So that was pretty much where I left off. There's really not much else to say about it. It's just a simple protocol, it looks pretty good. So before I go, I want to just mention one thing to anyone out there who is working with embedded systems. As this hopefully shows, security through obscurity does not work. Had this been properly cryptographically secured, it would have at least stood a chance at, resisting a simple, I didn't really attack it. I just looked at it for a few hours, right? It took me 5 hours to go from the time I picked the unit up to the time I had a Python script that could decrypt the entire communications with their head end. 5 hours, right? That's all it stopped me for, which is really not that much time at all. So if you're building an embedded system and you want to actually make sure that people can't reverse engineer it, do encryption, and don't make your own encryption. You've got to use something correct. I could go into side channel attacks like simple and differential power analysis and stuff, and you wouldn't believe how difficult it is to get encryption right. So, I'm sure someone at Anova thought that they were being really clever with their, rolling the bits by a different number for each byte. And by the way, it actually repeats. One thing I didn't mention is it repeats Once you get to six bit shifts, it then goes back to 0 bit shifts. So it doesn't mod 8, it mods 7. So it's a little bit interesting there. But I'm sure someone thought, oh, this is clever. No one's gonna really care that much. No one's gonna figure this out. And of course, it goes to show it. Of course, hackers are going to figure it out. If it's not mathematically impossible, if the developer can't reverse it without some secret, and the secret is unattainable, then of course, it's not secure. So I'll just mention that right there. This is a real world example of obscurity doesn't work. And of course, there are going to be people that argue that it doesn't matter. There are going to be people who say, well, it's just a cooker, right? It doesn't really matter. If someone can see this protocol or potentially intercept it or whatever. But I'll make the argument that you have no idea what this could be used for. You have no idea whether people could do denial of service attacks. I mean, if somehow someone could know your if someone could determine your device ID, then they could do a denial of service on your device by sending the API constant fake data, and then the device would effectively be useless for you. So I mean, there are always security implications, whether people see them right away or not. They're always there. So I'll just make that mention. So one thing that I mentioned in my hardware teardown, of course, is I kind of alluded to the fact that, what would happen if you put, now that we know what the wireless module is, this is from high-flying technologies, if we put that in the Bluetooth module, what happens? And of course, I'm pretty sure that you'd have to modify something in the EEPROM, so you'd have to modify it probably to know that it's a wireless device. But if it didn't, let's say that it was coded in such a way that it didn't have any config for that, and it just sort of detected that the wireless was there. If that's the case, then it probably still won't work if you just use their API, because it's probably going to connect, and they're going to be like, well, wait a second, we didn't produce this serial number to ever talk to the wireless, so maybe they block it or something. But if it's a big if, I mean, I'd probably give it less than a 10% chance that this would work. But if you were to put a wireless module in the Bluetooth version and you were to then redirect all the traffic to your own server, you could probably get wireless capabilities, Wi-Fi capabilities on the Bluetooth module. I'm not going to go into actually dumping the EEPROM or dumping the flash on the micro. That's a lot more effort, and it requires me to take the chip off and all that crap. I don't really want to bother to do that. I don't care. This is far enough for me. It gets me to where I want to go. If anyone wants to take this further, then be my guest. I'd love to know what you find. But yeah, I think this video is long enough, so I'm just going to stop waffling. If you have any questions, leave them in the comments. And yeah, so hopefully this was interesting. Hopefully you learned something. And as always, thanks for watching.